Okay, it's 9:40, so let's get started. Final week of recitations, so, woo. So quiz 13's out tomorrow. I made a column, entry in your gradebook of total quiz score as well as quizzes drop the lowest 3. So you should be able to see that. So currently it's out of 90. After this week, it'll be at 100. And I'm doing a final exam review, as I said last week on Thursday. Any questions before we start? Yeah.
Any recommendations on study resources?
There are plenty of study resources, so I'm sure you know quizzes are going to be very helpful. If you did homeworks, the solutions will be very helpful. Oh, and homework 5 solutions, we'll get them out eventually. I have one problem left to do, so we'll get those out. Midterm solutions, that's pretty obviously going to help. Past midterm solutions, past homework solutions, all the recitation solutions. I mean, there are plenty of resources available. And certainly the review is going to help if you have any particular question that you want answered. Yeah. Yes. And the format and point distribution is going to be exactly the same. 40 multiple choice, 5 long answer questions, 3 worth 10, 2 worth 15. Exactly the same. So you should know how to manage your time by now. Any other questions? Okay, so what did we talk about last week?
Decidability, reducibility.
Yeah, reducibility between what types of problems? Not decidable ones. Undecidable ones. So, yeah. I love when a pen works as well as this one. All right, so undecidable problems. So what were some of the problems that we talked about that were undecidable? ATM, the most famous of them all. ATM, and just like DFA, APDA, all that stuff, it's encodings of Turing machines that accept a particular input, some particular string. And we showed that this was undecidable. And the way we did it was, if we did have a way to decide that, then we can make a machine that could contradict itself. So that was the basic idea. So what was another problem we showed was undecidable? The ETM, proved it explicitly. So ETM was one. So it's just machines with empty language. So same idea as DFA, PDAs, all that, but we showed undecidability here via a what? How did we show that that guy was undecidable? It was alluded to earlier.
Wasn't it like we created an empty or a TM with empty language and then we proved that it was accepted?
Right. So the idea was, if we could solve ETM, then we can solve ETM. Okay. So that's called a. What was that called? If I can solve one problem, then I can solve another. What was that called? Reducing. Yeah. So we showed that ATM reduces to ETM. If I can solve this guy, then I can solve this guy. And if this guy is undecidable, then this one is as well, which is what we showed here. But what else did we do other than undecidable and reductions? What was one general thing that we were able to prove? So yeah, what is that called? Rice's theorem. So Rice's theorem. So what did that say?
Essentially that any Turing machine that has a non-trivial property about
Yeah, so we define property as based on what? What thing about, say, a Turing machine do we want to have a property of? Is it about the number of states or what? What was it about? I've done this probably 6 times now. It starts with L and ends with language. About the language of the Turing machines, right? So any non-trivial, so that means that there's some Turing machine that has the property, or really is in the language of the property we're talking about, and one that isn't. Any non-trivial property of the language of Turing machines. And by of the language, I mean that if you have 2 Turing machines with the same language, either both have the property or neither do. It can't be the case that there's some other deciding factor other than the language that decides whether one is in or out. Okay? It's undecidable. And how were we able to show this? Via a what? Reduction from. Yeah, ATM, it's the other way around. You reduce ATM to the property, but yeah, it is a reduction to that. So, any questions about these? So, can I prove ETM undecidable via Rice's theorem? Let's see. Is it a ignore non-trivial for a second. Is it a property of the language of Turing machines? Well, let's see. If you have 2 Turing machines with the same language, either they're both empty or they're both not empty. That means that either both are in here or both are not. So it is a language. It is a property of the language of Turing machines. Is it non-trivial? Yeah, certainly. You can certainly make a Turing machine that rejects everything, so it's in here, and you can make another Turing machine that accepts everything, and it's not in there. So, by Rice's theorem, I can say that ATM is undecidable. Can I prove ATM undecidable via Rice's theorem? Other than the fact that it's self-contradictory because we proved this via a reduction from ATM, but ignore that for a second. Can I prove ATM undecidable via Rice's theorem? Is it, well, and also, is it a property of the language of Turing machines? Yeah. Well, let's see. Can I have 2 Turing machines with different languages that accept the same string? Yep. So it's not a property of the language of Turing machines. So I can't apply Rice's theorem. And there's something hidden in here. It has to be only Turing machine descriptions. So you can't have anything other than Turing machine descriptions in the language. So here, because I have a machine and a string, that's not purely a Turing machine description, so it can't be a property of the language of Turing machine. So here I mean Turing machine descriptions. That's what I really meant. Whereas here, it only has Turing machine descriptions, so it is not immediately that I can't apply Rice's theorem. And then we saw from the other 2 things, yeah, you can apply it for ATM. Okay? Any questions about these? All right, so let's look at this problem. So we proved infinite DFA decidable last week, so let's prove this guy undecidable this week. So for these, at least these first 2, let's go both routes. Let's prove it via a direct reduction from whatever, and prove it undecidable via Rice's theorem if we can apply it. Okay? So let's do the easy one first. Can I apply Rice's theorem to this problem? So I'm going to have 2 problems. So Rice's. So let's see. Is this language consisting entirely of Turing machine descriptions? Yeah, that's pretty obvious. So that's a good, nice check. Is it a property of the language of Turing machine? Property of the language. Well, let's see. If we, so it's nice to write these down as checks. So if the language of some machine M1 equals the language of machine M2, well, could it be the case that one is in infinite TM and one isn't? Right here. Could it be the case that, say, M1 is in there and M2 is not in there? If they have the same language? No, because if M1 is in there, then its language is infinite, but that means that M2's language is infinite as well. So it must mean M2 is in there. Conversely, if M1 is not in there, well, it has finite language, so that must mean M2 has finite language, which means it's not in there. So M1, M2's descriptions are in, I'm going to abbreviate it, because I don't want to write it. Or either they're both in there, or they're both not in there. Okay. Sweet. So once I show that, what do I need to show next? Once I show it's a property of the language of Turing machine descriptions, what else do I need to show? There's one word I left out. Non-trivial. So if I want to show that this is a non-trivial property, what do I need to show? Non-trivial.
Possible for one machine to have the property.
No. Well, one machine to have the property, one to not have the property. So consider a Turing machine M1 that accepts everything, accepts all strings, and consider M2 that rejects all strings. What can I conclude about M1 and M2? No, from just M1 and M2. In relation to that language. Right, so M1 is infinite language, M2 doesn't, so that must mean M1's description is in there, M2's description is not in there. So from this, I can say that M1's description is in infinite TM, and M2's description is not in ITM, infinite TM. So I can conclude ITM is a non-trivial property. So from that, what do I need to say? Once I establish this non-trivial property, what should I say? It's undecidable via a what? By Rice's theorem. Those three words are the most important part here. Because what I've written here makes absolutely no sense until I apply Rice's theorem. Okay? So I should put this in caps, but I won't. By Rice's, by Rice's theorem, the language infinite TM is undecidable. So I would say you have to say by Rice's theorem because now you know you're applying Rice's theorem. Okay, so that's actually pretty easy. So all we did was we made sure it's a property, first off, that it's only Turing machine descriptions. That's pretty easy. If you have two machines with the same language, they both are in there or both are not. And for the second part, we made sure that there was one machine that had the property and one that didn't. So, and that was pretty easy as well. Any questions on how we applied that? Suppose I changed it, and I said, and M has at least 3 states. what would change? Can I apply Rice's theorem now? No. Why not? Because if I have two machines with the same language, I don't know whether they're both in or both out. Right? Because this one could have 5 states, this one could have 2. And that wouldn't tell me anything. So I can't apply Rice's theorem in this situation. Okay? But if I removed it, now I can. Because it's only about the language in this case. Okay? All right, so now let's actually do a real reduction. And then we gotta decide what language to reduce from. It actually won't matter what language we reduce from, but which one do you think would be easiest? Well, what does Rice's theorem use on the back end as a reduction? Yeah, ATM. So it might be a good idea to use ATM, and that's what we're going to do. But we're going to do an explicit reduction. And the nice thing is that if we can't apply Rice's theorem, this will always work. Okay, well, let's see. So what do I have to do in order to reduce from ATM? What do I need? Well, let's see. Let's go back here. What was the idea? If we can solve one problem, then we can solve the other. Which direction was that? Right, yeah. So if we can solve the problem we want to prove undecidable, like infinite TM, then I can solve the thing that I already know is undecidable, in this case, ATM. So by reduction from ATM, I mean we're reducing ATM to infinite TM. Okay. So what do I need to do once I know which kind of reduction I'm doing? Well, it was kind of said. If we know how to solve, in this case, infinite TM, then we can solve ATM. So how do I write something that's like, if you can solve this? What's that?
We assume we can solve it.
Right, assume we can decide that language of infinite TM. So let's assume we got to come up with a name for a decider, so let's call it D. Let's say it decides, I'm not going to write it again, infinite TM. So using D, what should I try to accomplish? What should I accomplish using D? Well, it said, if we can solve infinite TM, then we can solve ATM. So using D, what should I produce for ATM? A decider. Yeah. So let's see how, so we can then decide ATM as follows. So what is ATM, any decider, possibly a decider for ATM, take as input?
Machine description.
Yeah, so a Turing machine and some input. Yep. So on input and W, where M is ATM, and W is the string. I can't say that W is in the language of N because that's obviously not decidable. So I have to say W is a string. I don't know whether it's in the language of the machine or not. Okay? Well, let's see. I want this thing to be a decider, the thing I'm making. So it should say accept if N accepts W, and we'll say reject if N does not accept W. Well,
let's see, how am I gonna use my decider for deciding whether a Turing machine has infinite language? Well, if I just feed this machine n to d, does that tell me anything about whether m accepts w? It tells me nothing. Even if it had an infinite language, it could accept every single string there is except w. So that doesn't tell me anything. So what should I do instead? Let's see. Maybe we can make a machine in here that has infinite language or does not have infinite language, depending on what condition. Whether n accepts w. So let's see. Let's make a machine that has infinite language if m accepts w, and finite language if it does not. What's our favorite infinite language? Sigma star. So maybe what we can do is, let's not accept anything unless m accepts w. At that point, we could accept everything. So let's try that. So let's construct ATM m prime. And so this thing can take anything as input. So let's call it x. Well, let's see. I only want to accept x if m accepts w. Well, once I make this machine m prime, is the fact of whether m accepts w fixed? Once I'm down to this first step, is the fact of whether m accepts w fixed? Yeah, because once I have these machines, they're fixed. So the answer of whether it will accept or not is either going to be true or false. So if let's just see, if I simulate m on w, that's going to either stop or run forever. I don't know. It's not some variable type thing. It's fixed. So let's just say that it really does accept. Then, what was our step after here?
If it accepts.
Yeah.
Make m prime.
Yeah, so if m accepts w, then we should accept x. Well, let's see. If m really does accept w, what is m prime's language? If m really does accept w, what is m prime's language? It's infinite. It's actually everything. Because if it really does accept w, this statement right here will always be true, regardless of what x is. So I will accept no matter what input I feed m prime. So m prime's language is infinite. Well, think about the other case. If m does not accept w, either via rejecting or running forever, what is the language of m prime? It must be empty, because I can never get to this accept x part. So there's no other way to accept any input by m prime. So therefore, it can't accept anything, and therefore it's finite language. So this is the only part of the machine. Now, once I make that machine, what should I do with it? Yeah, feed it into D. Yep. Wait, but let's make sure I'm not cheating here. Can I actually do that first step? It has a simulate M on W part in there, and that could take forever. right? That's certainly possible. Is there something wrong here? Am I actually running M prime? Nope. I'm just saying, make this machine for me. Okay? I'm not actually running it. I'm assuming that this decider can take whatever Turing machine and decide it for me. I don't know how it works, but I'm assuming it exists, and therefore it must stop, no matter what. All right. So then run this decider D on the description of that prime. And because D is a decider, it must say accept or reject. So if it accepts M prime, and then the other case whether D rejects. Well, let's see. If this decider, this supposed decider, says, yeah, M prime has infinite language, what should I say to my supposed decider for ATM? Accept. Because the only way it could have had infinite language is if we hit this accept X part, which meant M accepted W. Since I'm trying to decide whether M accepts W, I should say accept. So now let's think of the other case. If this decider says, no, you have finite language, well, what do I know about M and W if M prime has finite language? Could M have accepted W? No, because if it did, I would have accepted all possible string sets. And I know it has finite language. It actually is empty, but it has finite language. That's the important part. So it has finite language, therefore M did not accept W, so I should say reject. Okay. Super. Any questions about that? What if I reintroduced that other condition? Where it had at least 3 states. So 3 is not important here. But could I modify, obviously we can't apply Rice's theorem now, but can I do this reduction now? Yeah, what do I do? Well, what would I have to say here to change it so that it works?
Step 1, check the 3 states.
Yeah, so if D, well, I better make sure that, yeah, I should check that M prime has at least 3 states. If it does not have at least 3 states, could I just add an arbitrary state? Yeah, so that's easy.
We need to change anything because D decides ITM. Wouldn't that therefore decide that it already has 3 states?
Yeah, but it could be the case that M prime, well, this part certainly will have more than 3 states, but I can't guarantee that. I could have made this 10 trillion states. And then therefore I could, but what I would have to do in that case is I would just add as many states as I need. So then in this particular case, so this is like 1.5 steps. Add states to M prime as necessary. Something like that, yeah. So I can't apply Rice's theorem in this case, but I can do a reduction still. So that's why reductions are so much more powerful, but Rice's theorem is far easier. But it can't be applied everywhere. Okay? Any questions about these?
At the end of that, would we need to then state by ATM it's
Yeah, oh, thank you. So therefore, assuming D, then ATM is decidable, but it is not decidable. So infinite TM is also undecidable.
right down to the corner.
Yeah, so you're correct. You would have to say, based on this reduction, then I can say something about whether infinite TM is undecidable. Because I know ATM is undecidable, therefore infinite TM can't be decidable. Thanks. Any other questions about these? Okay, so let's do another one. So this is on a past recitation that I've done, I think, a year ago. And it's all Turing machine descriptions where the machine accepts the empty string. Okay? So it's not quite ATM, it's a particular string that I'm worried about. Okay? And this is undecidable as well. So can we apply Rice's theorem in this particular case? Yeah, well, let's check. Does it only have Turing machine descriptions? Yeah. So that's a good check. If so now we gotta check if the language of M1 equals the language of M2. Is it the case that both of them are in or both of them are out? Yeah. So if they have the same language, either the empty string's in there or it isn't. So therefore both are in or both are out. Yep. So this is very similar. Well, what about the second part where I have to say that there's a Turing machine in there and there's another Turing machine not in there? Yeah.
So if they both have the same language, they're not in or out equally, then you can't use Rice's theorem.
I can only say something about whether they have the same language or not. Yeah. So if they have the same language, either the empty string's in both of them or it isn't.
But I mean, like, if they have the same, like, just different, I guess, example. If they have the same language, but only one of them is in,
But then you can't apply Rice's theorem. Yeah, just like over here, it could be the case that one of them is in and one of them's out, even though they have the same language. But here I can because they have the same language, both are in, both are out. Yep. All right, so the second part, I have to find a Turing machine that's in there, one that isn't. Any particular choice, the remaining there.
but you still have the same.
Yeah, they do the exact same Turing machines. So, same as the first one. Okay, easy. So now what can I conclude? It's undecidable via Rice's theorem. So by Rice's theorem, I should put those three words on a plaque. Yeah, by Rice's theorem, ESTM is undecidable. Super. So you see how easy this is. But let's do an actual reduction, just in case. So let's do a reduction. What problem do you think would be easiest to reduce from? How about ATM again? Why not? Let's try it. So let's do reduction from ATM. So again, is ATM reduces to ESTM. Right. So assuming a decider for ESTM, then I could then make a decider for ATM. Well, so then we gotta suppose that there is such a decider. So suppose D decides ESTM, then we gotta make a decider for ATM as follows. And then it starts off the same. So on input MW, same condition, I'm not going to write it. What do you think would be a good strategy here? So I'm gonna suggest a strategy similar to here. So we want to check whether or not using this decider, whether some Turing machine has the empty string in it or it doesn't. So a nice idea is start off with a Turing machine that does not satisfy this. Okay, so like we made a machine before, start off before you even consider M and W. Start off with not being in this language. So in this case, it would be like accept nothing or something like that. Then you run M on W, and then satisfy this. Okay. So let's see. So we're gonna construct ATM M prime with X as before. Let's see. At this point right now, what is M prime's language?
We really
Well, I'm building the thing. Have I accepted anything yet? No. So is the empty string in M prime's language yet? No. So we're fine. So we already have a machine that doesn't satisfy this property yet. So, yeah.
When we say construct the TM, we assume that there's no accept states.
What do you mean there's no accept states?
Well, it's just like you're just construct the TM and prime. Or like we know that the language is empty.
So far.
That it's always
So far.
empty.
I haven't finished yet.
We always assume like right when we construct it, it's empty.
Yeah. So yeah. It depends on the property. So sometimes right at this first step you say if X is some string, then accept it. Then the next step you run M of them. But here I already satisfied what I didn't satisfy the property, so we're fine. All right. So now what should I do? Now I gotta check if M accepts W, then what string should I accept? Well, it doesn't actually matter in this case. So run M on W. If M accepts W, what should I do? Well, at this point, if it accepts W, I better have the empty string in there. So there are two ways you can approach this. What should I do here if M accepts W? You could just accept X. So let's see why that's true. If I accept X there, so let's suppose M accepts W. What is the language of M prime? It must be infinite, just like we did before. Well, it's actually what language? It accepts everything. So its language is sigma star. So is the empty string in sigma star? Yeah. Well, consider the case if M does not accept W. What's the language of M prime now? It's empty. Because if it does not accept W, there's no way I could accept X at this point. There's no other place I could accept X. So this will actually be enough. Because I could actually run the decider from before, but I could actually run the decider here too. It works exactly the same. Another way you could approach this is, at this point you could say, if X equals empty string, accept X. Otherwise, reject X. So this is another
what alternative to doing this?
Then the only two possible languages of M prime are empty and just the empty string. And then therefore, my decider would still be able to tell the difference. Okay. So with this machine, what should I do with it? Run the decider D on this machine M prime. We'll run D on M prime's description, and then we again have two cases. If D accepts, then we get something. If D rejects, we get something. Well, if D accepts, then that must mean what about M prime? It accepts the empty string. Well, the only way we could have accepted the empty string is what? If M accepts W. And I'm trying to decide ATM, so I should say accept. Yep. So that's just a handy way of saying, yeah, M did accept W. If D says no, the empty string is not in M prime's language, then what can I conclude from that? It couldn't have accepted anything because if M did accept W, then it would have accepted the empty string. But if it didn't accept the empty string, it couldn't have accepted anything else. That must have meant M did not accept W. So I should say root. So it's almost exactly the same. The only difference was how we were able to construct this machine, but everything else followed exactly the same. So that's actually one of the reasons why a lot of people are scared of reductions, but a lot of the reduction structure is exactly the same. So that makes it very nice. But any questions about these? All right, so let's look at this. So I have to tell you, how many of you know CSE355? The graduate version of this class? So this next problem actually appeared as a homework problem when I took it, and I thought it was pretty interesting. So here's the idea. So if we consider this function, L of n, is all it is just the length of the strings in L of n. That's all it is. And then the language reglen TM is just all the machines. M is ATM, and this function on M is regular. So the idea is if you consider all the lengths of the strings as actual strings, so just a bunch of ones, then this language of just ones is regular. Okay? So for instance, if this machine accepts every single string, then it has some string of every single length. Therefore, this L of M has every single string of ones that's possible, so therefore it's 1 star in that case. But you could have, say, only a subset of 1 star, and it'd still be regular. But unfortunately, this is undecidable. So this language is kind of similar to checking whether a Turing machine accepts a regular language or not, and that's undecidable too, but this is a different formulation. All right, so it's undecidable. What do you think I should try first? Let's use Rice's theorem. So can we apply Rice's theorem to reglen TM? Well, is it a language that has only Turing machine descriptions? Yep. So that passes our check. First check. If I have two machines with the same language, do I get both in, both out again? Well, let's think about it for a second. If they have the same language, is L of this function, L of M1, equal to L of M2? Yeah, so from that I know L of M1 equals L of M2. So now is it, can you figure out whether they're both in or both out from this? Well, if they're both equal, their languages, I guess, is it the case that they're both regular or not? Or could it be that L of M1 is regular and M2 it isn't? No, because they're equal. So this means L of M1 is regular and L of M2 is regular or is not regular, and therefore that's all we need. Okay. Super. Now, can I find, so this one will be actually a little more challenging than the last two, but can I find a machine that accepts lengths of strings that's non-regular? So there are actually many examples, but is there a unary language to make it easy? Is there a unary language that we saw that was non-regular? How about prime lengths? Yeah, so consider the language. 0 to the p, where p is prime. We showed that this wasn't even context-free, so therefore it can't be regular. Can I make a Turing machine to decide that? Yeah, but we actually showed it, I think, 2 weeks ago, or 1 week ago. So, be the language of M1. Then from that I can conclude M1's description is not in reg-length because this language is essentially the same thing as L of N, but the only thing is that zeros are swapped for ones. So L of M1 in this case wouldn't be regular because I know the original wasn't regular. But now, can I make a Turing machine that the lengths of the strings is regular? Yeah, how about the Turing machine that accepts nothing? Yeah, the lengths, this lengths language, there's nothing in it, so therefore this lengths language is empty, and the empty language is regular. So consider M2 that you could do accepts everything, it works the same way, but rejects rejects everything, then we know M2 is in reg-length. Okay. All right. So now what can I conclude? So this by Rice's theorem, it's decidable. So by Rice's theorem, reg-length m is minus 9. Super. So we had to work a little harder here because just to understand the problem was a little bit more. But we had to do a little more work here in finding a machine that accepted things that wasn't that wasn't regular, and we knew one that we did earlier. Another one you could have done was the perfect squares one. That's also one that we saw that was non-regular. You don't have to limit yourself to unary languages here, but I figured it was much easier because the translation from here to L of M is just swapping a 0 for a 1. So there's absolutely no change there other than that. So the conclusion was a lot easier to get from there. But you could have chosen something else as well. Any other last questions? So thank you for coming to my recitations. It was a blast. Thanks.
Sign the sheet if you haven't.